Lesson 20, uniform circular motion in the vertical plane. Okay, so vertical uniform circular motion. So before this, we were talking about, spinning things like, above your head. Um, so yeah, vertical. Or so horizontal. Now we're going to be talking about spinning things vertical. And there's a difference because when you're spinning things horizontally, really there's only one force involved, right? There's the force of tension or that force of um, uh, friction or like the types of things that we did last time, right? But now when you spin things vertically, there's going to be two things that add up to be the centripetal force. So what we're going to do though to make things a little bit easier is we are going to call things going toward the center of the circle positive and away from the circle negative. So, not the typical, this is positive, this is negative, this is positive, and this is negative. It's going to be toward the center of the circle is positive, away from the circle is negative. That's good. It's just going to be helpful. We could do it the other way too. It's just you have to keep track of your symbols a lot more and it gets a lot tougher. So if we kind of look at this situation where at the top of the circle, the weight is acting toward the center of the circle, the tension force is relatively small. So we're saying that the force of gravity and the tension force are working together to make up that centripetal force. Okay, so let's kind of think about this um, as it's going around in the circle, right? So we've got, this is it's a circle this direction now in the vertical plane is what we're talking about, right? So in order for something to be going into in a circle, there needs to be a centripetal force, right? Something needs to be making up the centripetal force. And if there's not something making up that centripetal force, then what happens is it falls, right? It stops going in the circle. It's only when there's enough centripetal force adding up that it goes into its circle. The two things adding up to make this thing go into a circle right now are the force of gravity pushing down and the force of tension pulling in. So, and at different points of this circle, there's going to be different combinations of which one's bigger. So at the very top of the circle, so if I stop this and think about this thing at the very top of the circle, then pretty much everything here is the force of gravity. The centripetal force that's required to keep this thing going in the circle is almost entirely gravity. The tension is like pretty much let off at the top. Unless I'm spinning it really fast, then it's still really tight if it's spinning fast. But it's mostly gravity at the top. But then what's going to happen at the bottom, right? At the bottom of the circle, the gravity is pulling away from the center of my circle, right? So at the bottom, it's actually not being helpful at all. Gravity is actually making it pull away from the circle. So what needs to happen is that the tension in the rope needs to make up for that. The tension in the rope gets really tight at the bottom because it needs to add up to that certain centripetal force that it needs to go into a circle. Hopefully that made sense. I know I'll show you on paper here in a second. It might make a bit more sense too. Okay, so back to the paper. So we start thinking about this as an equation. The net force, the overall force, is just going to be the force of gravity plus the force of tension. That net force is our centripetal force. The overall force is going to be what's causing this thing to go in a circle. So now at the very top of this thing, the centripetal force is going to be Fg, which is going down, right? So we're going to call it positive, plus Ft, which is also going to be positive because it's going toward the center of the circle. So the two of those added together is going to give you what the centripetal force is. So those two things together give you this. Okay, at the bottom of the circle, we've got Fc is going to be equal to Fg plus Ft. But in this case, like I was showing in the demo there, we need to have a force that would add up to be. We're going to make our arrow for centripetal force. Well, I guess it's smaller in that one. It's going to be that, right? In order to make up that, right, Fg is pulling away from our circle. It's not helping at all. So Ft needs to make up the extra slack, right? It needs to apply more force. so that we can still carry on having that centripetal force being what it is to make it go in a circle. If this thing is traveling at a certain speed, that centripetal force, so the net force, is going to be the same all the way around, or the magnitude would be the same. They're in different directions, but the same magnitude. And that's just what I said here too, right? Uniform circular motion requires a constant centripetal force. And that's uniform, right? So if our speed was changing as it was going in the circle, then it wouldn't be uniform. So we're talking about like a constant speed going around in the circle. All right, so let's see if we can make some sense of this. So it says a 1.8 kilogram object is swung from the end of a 0.5 meter string in a vertical circle. If the time of revolution is 1.2 seconds, what's the tension in the string? At the top of the circle and at the bottom of the circle. So for uniform circular motion, we can treat this like just like our last lesson, right? For the first part, we got to figure out what FC is. It's going to be the same at the top and the bottom. It's what makes FC up that's going to change, right? So we can figure out FC just by, just like in last lesson, just plugging in the numbers where they belong. So FC ends up being 24.67 newtons. Okay, we can also calculate Fg right off the bat, so we just know that. Fg is just mass times acceleration due to gravity. And then all we have to do is make our formula. So at the top, the net force, or the centripetal force, is going to be Fg plus Ft. Now, they are both going toward the center of the circle, so we're going to say they are both positive. So Fc is going to just be adding up Fg and Ft. If we rearrange this formula now for Ft, we get Fc minus Fg, which is just 24.67 minus 17.66. So the force of tension is going to be 7.01 newtons. At the bottom, it's really the signs that change, and that's it. So the centripetal force, we're going to start off with, it's going to be Fg plus Ft. Now if you put the symbols to it, Fc, which is toward the center, it's always going to be towards the center, right? It has to be, so it's always going to be positive. But then Fg this time is pointed away from the center of the circle, so we're going to call it negative. And then that's going to be plus the force of tension, which is pointing toward the center of the circle. If you rearrange this for Ft, then we get Fc plus Fg is going to be equal to the force of tension. So the force of tension has to be bigger than the centripetal force to overcome that gravity pulling it away. And that's 42.33 newtons. So just while we're on this note, where do you think the string would be most likely to break if you were spinning something around in a vertical circle? Well, you can see from the numbers, right? At the top, it's going to be that. At the bottom, it's going to be the biggest it's going to be. So the force of tension is the biggest at the bottom of the circle. So it's going to break at the bottom. Okay, so now before we do the next one, I just want to give you a kind of visual of what's happening here. It's going to say what's the minimum speed that something can go around a circle. So that could be like a roller coaster going around a loop. This could be like, the minimum speed that this could go before it drops like that, right? Like that's not a circle. We want, what's the minimum speed that this thing's going to continue on in a total straight, or in a total circle. So if you look at this though, when it's right at the top, this pretty much the tension in the string goes totally relaxed, right? So that's what we want. We want when the tension in the string is 0. That's going to be the minimum. So what we want to do when we start doing our equations here is we're just going to make the Ft part of it equal to 0. So at that point, right at the top, Fc, the centripetal force, is equal to the force of gravity. So that's the kind of key bit of info there. So example 2 says an object swung in a vertical circle with a radius of 0.85 meters. What is the minimum speed of the object so that it remains in circular motion? Okay, so the position where the minimum speed can be calculated is at the top of the circle, right? That's going to be where we know Ft is equal to 0, right? If the speed is less than the minimum, the object will fall out of the circle. So just pretty much like I was saying there. So what we're going to do is say, okay, ft is equal to 0. So now fc is equal to fg. Now what I'm going to do is just replace fg with mg, because that's what Fg is equal to, mass times gravity. I'm going to replace Fc with mv squared over r, because that's the equation for Fc and has the stuff that we're interested in, right? R, and I'm looking for V. And what the big thing here is that we kind of have to start doing our equations like this. I can't just find Fc, or I just can't find Fg and then plug in what I know like we've done before. Because in this equation, it doesn't actually give you the mass of the object, right? But now that we've done it like this, I've got mass in the top of the equation on the right side. I've got mass on the top of the equation on the left side. So if I divide both sides of the equation by m, the masses cancel. So all of a sudden now we didn't even need mass, right? So now all I got to do is rearrange what I have left here for v. So v is equal to the square root of g times r. So the minimum speed is going to be 2.89 meters per second. All right, so that's going to be it for that video. I'm going to do the practice problems in the next one. So I'll see you guys in that one.